Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel, and today's topic of discussion is basic parallel circuits. Our objective today is to take a close look at parallel or side-by-side electrical relationships and discuss basic properties for parallel configurations. We'll learn that voltage across elements placed in parallel is the same. We'll make use of this incredibly simple statement to determine unknown properties based off limited observations. Additionally, we'll discuss how current and power is proportionally distributed within a parallel circuit. And finally, we'll discuss instrumentation used to measure parallel circuit properties and parallel circuit applications. This lecture serves as an introduction to parallel circuits only. Later lectures in this same playlist will introduce and discuss Kirchhoff's current law and the current divider rule, two incredibly useful circuit analysis skills applicable to both basic parallel relationships and more advanced scenarios. Today we'll discuss basic parallel properties only. However, understand this introductory level discussion is essential and, most importantly, true and relevant at all levels. Voltage across elements in parallel is the same. At no point will I ever bait and switch you nor backpedal this basic statement. This will hold true for basic DC circuits as well as later discussion on AC circuits. Regardless of the flavor, voltage across devices hooked in a parallel relationship is the same. This property makes sense if there are only two nodes that define a parallel connection, and by definition, voltage is a two-point measurement. How could there be a difference? If a single voltage source is asked to supply several different devices, all requiring the same voltage, a parallel relationship enables this possibility by providing two nodes across which an identical voltage differential occurs. This is an incredibly important application of our first parallel principle that voltage in a parallel relationship is the same. It allows electrical loads to function independently of one another, all supplied by a single voltage source. Additionally, we'll learn about current distribution in parallel arrangements and that such networks enable the connection of powerful generators to a common distribution network, all sharing the same value. We'll return to these subjects later. For now, let's stick to the basics. Voltage across elements in parallel is the same. We've already introduced resistance calculations for parallel relationships in the fixed resistors lecture, available at the Big Bad Tech channel. If you haven't watched this lecture yet, or only dimly recall its contents, I'm suggesting you take the time to watch it now. You may as well familiarize yourself with Ohm's law while you're at it, since we'll be applying it over and over during the course of this lecture. If you'll recall, a parallel relationship is a side-by-side relationship, and that a pair of nodes serves as a point of common connection for two or more two-terminal devices. The dead giveaway to such a construction is that flowing current now has a choice about which path it follows. This is in contrast to our previous discussion about series relationships, in which there exists a single path. We'll return to a more thorough comparison of the similarities and differences between series and parallel configurations in a moment. Before we begin with a technical discussion of parallel relationships, let's just briefly examine the manners in which such relationships can be depicted in schematics. Again, one of the most useful techniques I've found in teaching basic circuit analysis is to view the circuit from the perspective of flowing current. As current enters a node, ask yourself, does current have a choice of paths? And if so, how many choices? If there exists no choice, the elements connected to this node are in series with one another, and there exists one path. If there exists a choice, the branches connected to this node are in parallel. The upper left circuit is a parallel combination of two resistors, a 1 kΩ resistor and a 2.2 kΩ resistor. The upper right is also a parallel combination of two resistors, only this time it's drawn horizontally. It's a parallel combination of a 1.2 kΩ resistor and a 1.8 kΩ resistor. The lower left is a parallel combination of three resistors, a 1.5 kΩ resistor, a 1.2 kΩ resistor, and a 6 kΩ resistor. The lower right circuit is also a parallel configuration of three resistors, although it's drawn slightly differently. It's a 2.4 kΩ resistor, a 4 kΩ resistor, and an 8 kΩ resistor. I know there seems to be a bunch of additional paths in this schematic, but in reality, it's still only two nodes used as a common point of connection for all three two-terminal components. We'll return to the utility of such alternate depictions of parallel circuits when we discuss Kirchhoff's current law and the current divider rule in later lectures. Recall from the fixed resistors lecture that the total resistance seen by a source for a parallel combination is always less than the smallest resistor composing said parallel relationship. Additionally, those resistors composing said parallel relationship can be exchanged without affecting the total resistance. The resistance of a parallel combination can be calculated using one of two formulas, one of which I have extreme affection for, and the other nothing but extreme loathing. Use whichever method floats your boat, but I am telling you, your boat will sink if you use the sum of conductances formula, because it is terribly easy to mess up the order of operations and get a wrong answer. Additionally, we're aware of a shortcut pertaining to identical resistors in a parallel relationship, and that the total resistance of a parallel combination of identical resistors is the value of the identical resistor divided by the number of individual occurrences of that identical resistor. For example, 5 20-ohm resistors in a parallel combination has a total resistance of 20 ohms divided by 5, or 4 ohms. It's been a while since we've employed these parallel resistance formulas, and I'd hate for you to pull a muscle in the middle of this lecture. So let's do a couple warm-up exercises by knocking out these example problems before we begin. Pause the lecture and take your best shot at this. I am not going to do a thorough step-by-step review of each individual problem, since this is a prerequisite skill. However, if you're looking for an in-depth use of these formulas, again, check out the fixed resistor lecture available at the Big Bad Tech channel. The first parallel combination in the upper left, a 1 kilo-ohm resistor in parallel with a 2.2 kilo-ohm resistor, should yield a total resistance seen by the source of 687.5 ohms. Notice the total resistance of this parallel combination of two elements is less than the smallest resistor within the parallel combination. The second parallel circuit in the upper right-hand corner is a 1.2 kilo-ohm resistor in parallel with a 1.8 kilo-ohm resistor, yields a total resistance seen by the source of 720 ohms. The total resistance seen by the source for the parallel circuit in the lower left-hand corner should be 600 ohms. I'll take a brief foray into the mathematics surrounding this calculation to point out three properties. Number one, that the order of resistors in a parallel relationship can be exchanged without affecting the final outcome. Number two, the fact that identical resistors in a parallel relationship can be simplified using a shortcut. And finally, three, one can use the two-resistor formula to calculate total resistance of a parallel combination consisting of more than two resistors and gain intermediary results. Using the two-resistor formula on this circuit and the fact that order of engagement does not affect the outcome allows us three different paths to reach this same goal. Method 1. First, we can take R1 and R2 in parallel and simplify those as an imaginary resistor I'll call R', where R' is approximately 666.7 ohms, and our total resistance is the parallel combination of R' and R3 at 600 ohms. Method 2. We can take R1 and R3 in parallel and simplify this combination as an imaginary resistor I'll call R', where R' is a 1.2 kilo-ohm resistor. This imaginary resistor R' is in parallel with R2, also a 1.2 kilo-ohm resistor. We can use the two-resistor formula again, or make use of the shortcut that identical resistors in parallel equal the resistance of the identical resistors divided by the number of occurrences. Two 1.2 kilo-ohm resistors in parallel is 1.2 kilo-ohms divided by 2, again yielding a final answer of 600 ohms. Method 3. Finally, we can start by taking R2 and R3 in parallel, and combine them into a single imaginary resistor I'll call R', where R' is 1 kilo-ohm. R1 is then taken in parallel with R' to again yield a final answer of 600 ohms. Finally, since some of you insist on being hard-headed and using the sum of conductances formula, we realize that 1 over 1.5k plus 1 over 1.2k plus 1 over 6k is also equal to 600 ohms. At this point, I'd like to take a moment to make very clear the following important observations regarding parallel circuit resistance calculations. the total resistance of our parallel combination is less than the smallest resistor. We can make use of the 2-resistor parallel formula for combinations of more than 2 resistors with the additional benefit of obtaining intermediate values. Additionally, we can exchange the order of resistors in a parallel combination without affecting total resistance. We can make use of an identical resistor shortcut. We can, if we're unusually hard-headed, use the sum of conductances formula to solve for the resistance of a parallel combination of resistors in one mouse calculation event. And finally, and most importantly, regardless of the formula used, the sequence of engagement, the shortcuts applied, or your age, gender, race, class, or sexual orientation get the same answer, and it should be correct. If at any point any of these methods were improperly applied, one or more of our paths would have yielded a contradictory answer. The point is, there exist many means to check your work. If you've got the time, it's a great idea to do so. Yes, it'll take twice as long if you're doing 2 sets of calculations. But what do you want? Right answers or wrong answers? In this spirit, you're on your own for our last combination of 3 parallel resistors in the lower right-hand corner. If you've done it correctly, you should have gotten close to 1,263.2 ohms. If you're getting 791.7, you did the sum of conductances formula and you did it wrong. Alright, now that we're warmed up, let's dive into a discussion of parallel circuit properties. The most important property being that voltage across elements hooked in parallel is the same. Let's make use of this property and use it to calculate desired unknowns like voltage, current, and power. Taking our first 2-resistor parallel circuit and supplying it with a 140 volt DC source, let's see if we can determine the voltage across each component, the current through each component, and the power dissipated by each component. I'm intentionally asking you to hold off on determining the current and power supplied by the source for a reason. I've got a trick up my sleeve that is going to require me leading you around by the nose for a bit before I reveal it. Trust me, it'll be worth it. Remember, anticipation is part of showmanship. Before you run off and calculate the other results, though, stop and pause to consider your expected results. Should voltage across any element hooked in parallel be different? Absolutely not. Voltage across elements hooked in parallel is the same. If you encounter any variances of these expected results, you are doing it wrong. If you're bold and daring, by all means, pause the lecture and take your best shot at this. However, since this is the first time we've done parallel circuit calculations, I don't blame you if you watch me this first go around. Then away we go. Voltage across elements hooked in parallel is the same. The supply voltage E is providing a differential of 140 volts between nodes A and B. The 2 terminals of the 1 kilo ohm resistor are between nodes A and B, as are those of the 2.2 kilo ohm resistor. If the difference between A and B is 140 volts, it stands to conjecture the difference across components hooked to the nodes A and B is also 140 volts. Don't make this hard. Voltage across elements hooked in parallel is the same. The voltage across the 1 kilo ohm resistor is 140 volts. The voltage across the 2.2 kilo ohm resistor is 140 volts. If you want further proof of this, we can use Kirchhoff's voltage law to demonstrate that the sum of rises equals the sum of drops for any loop in this relationship. Start here. Travel in this direction. Rise E, fall V1K. Start here. Travel in this direction. Rise E, fall V2.2K. It can be said that our Kirchhoff's voltage law equation yields E equals voltage across the 1 kilo ohm resistor, which equals the voltage across the 2.2 kilo ohm resistor. We can use Ohm's law to find the current through the 1 kilo ohm resistor, where the current through it is the voltage across it divided by its resistance. 140 volts divided by 1 kilo ohm yields 140 milliamperes. Similarly, the current through the 2.2 kilo ohm resistor is the voltage across it divided by its resistance. 140 volts divided by 2.2 kilo ohms yields a current draw of approximately 63.6 milliamperes. The power dissipated by the 1 kilo ohm resistor is equal to the voltage across it times the current through it, or any permutation of the power equation. 140 volts times 140 milliamperes yields 19.6 watts. Obviously, we're not dealing with itty-bitty half-watt carbon film resistors on protoboards anymore. Chances are we'd have to step up to a wire-wound resistor. Using similar techniques, the power dissipated by the 2.2 kilo ohm resistor is equal to the voltage across it times the current through it, or any permutation of the power equations. Yields approximately 8.9 watts. Notice we solve for all desired unknown quantities using previously understood properties like Ohm's law and the power equations. The only new property we utilized was the very simple and very easy to remember statement that voltage across elements hooked in parallel is the same. There is no formula for parallel circuits. There is the simple truth that elements hooked between two nodes must necessarily experience the voltage differential between those two nodes, since voltage, by its definition, is a two-point measurement. This statement is incredibly simple, yet useful beyond measure. For those with an interest in efficient and timely calculations, notice at no time did solving for voltage across, current through, and power dissipated by individual components within this parallel network necessitate you solving for total resistance of this parallel combination, despite the fact that we did so in one of our earlier warm-up exercises. This combo, if you recall, exhibited a total resistance of 687.5 ohms. I'll let you in on a little secret. Very rarely, if ever, do you need to solve for the total resistance of a parallel combination of elements if you can simplify a complex circuit to a purely parallel relationship. You may have to solve for the resistance of a parallel combination inside the complex circuit. However, once you reach the base level of simplification as a pure parallel circuit, it's often better to simply resort to the most fundamental of parallel properties. Voltage across elements hooked in parallel is the same. You'll appreciate this time-saving step when we enter series parallel circuit analysis. If you think about it, it's almost like these two resistors are two separate renditions of simple single-element Ohm's law calculations with no relation to one another. Does the 1 kilo ohm resistor care what the 2.2 kilo ohm resistor is doing? I doubt it. As long as this 1K is drawing 140 milliamperes from a 140 volt source and dissipating 19.6 watts, it's totally cool with its crazy neighbor throwing loud house parties, hosting cockfights, and letting off fireworks. That's kind of the point of a parallel relationship. These two resistors could be two totally different electrical loads. The 1 kilo ohm resistor could be a heater, and the 2.2 kilo ohm resistor could be a fan. If you want to turn on your heater, connect it in parallel to a 140 volt source. If you want to turn on your fan, connect it in parallel to a 140 volt source. The heater doesn't care what the fan does, nor does the fan care what the heater does. Why you'd ever try to heat something up and simultaneously cool it off with a fan is a little odd though, but the electrical loads don't care. Who does care though? My bet is that the source, i.e. the electrical company, now supplying two electrical loads instead of one, does. Aha! It is now time to take a look at parallel relationships from the perspective of the source. I told you anticipation was worth it. Let's look at the source using two different approaches, the hard way and the easy way. Here's the easy way. Where did the current supplying the 1 kilo ohm resistor come from? It obviously came from the source. I'm not even going to ask this same question about the 2.2 kilo ohm resistor, because it's pretty obvious that this current was supplied by the source. If the 1 kilo ohm resistor was drawing 140 milliamperes from the source, and the 2.2 kilo ohm resistor was drawing 63.6 milliamperes from the source, how much current was drawn from the source? It's pretty obvious that the source would have to supply I1K plus I2.2K for a total current draw of 203.6 milliamperes. Does the source care what these two resistors are doing with that current? No, it's just supplying 203.6 milliamperes as if the parallel combination of our two resistors were just some imaginary resistor I'll call R prime. Just out of curiosity, What might be the resistance value that draws 203.6 milliamperes when supplied by a 140 volt source? Ohm's law states that 140 volts divided by 203.6 milliamperes yields a total resistance of 687.5 ohms. Oh my gosh. That's what we just calculated using the parallel resistance formula. Yet at no point did I directly apply it during this set of calculations. I used Ohm's law, the simple and non-negotiable statement that voltage across elements hooked in parallel is the same, and a pretty understandable observation that current drawn by individual elements within a parallel relationship had to come from somewhere. This property bears further inspection. The current coming out of node A is 140 milliamperes and 63.6 milliamperes. Therefore, 203.6 milliamperes must have come into node A. The single resistor simplification makes this readily apparent. What goes out must necessarily come in. Additionally, since we're aware that an electrical circuit, as the name implies, requires a return path, it means that 140 milliamperes and 63.6 milliamperes enter node B, and it means that 203.6 milliamperes must come out. What goes in must come out. This is Kirchhoff's current law, something we'll examine in great detail in a later lecture. However, you'll be happy to know it really doesn't get more difficult than this. What goes in must come out. What goes out must have come in. Not only does Kirchhoff's current law aid in circuit analysis, it is also a useful sanity check in that current coming out of a node can never exceed that coming into it, nor can current entering a node not leave it. The sum of current inputs always equals the sum of current outputs. It's almost like Kirchhoff's voltage law in reverse. Kirchhoff's voltage law looks at voltage rises and drops using a loop. Kirchhoff's current law looks at current inputs and outputs using nodes. Let us now consider the magnitude of the current drawn by individual elements in relation to their resistance value. The 1 kiloohm resistor draws 140 milliamperes. The 2.2 kiloohm resistor draws 63.6 milliamperes. Notice how the incoming current splits inversely proportional between the two electrical loads. The 1 kiloohm resistor, being the smallest resistance supplied by the same voltage, draws the most current. The 2.2 kiloohm resistor, being the largest resistance supplied by the same voltage, draws the least current. Understanding Ohm's law and our newfound appreciation for basic parallel properties, we can therefore state that the smallest resistor will draw the most current and the largest resistor the least. If two identical resistors were hooked in a parallel relationship between two nodes with the same voltage across them, it stands to conjecture that the identical resistors in a parallel relationship will draw equal amounts of current. Having solved for source current using basic understanding of Kirchhoff's current law, i.e. the easy way, we've yet to solve for this same quantity the hard way. The hard way of solving for source current is a good old-fashioned Ohm's law slugfest where you just hit the problem repeatedly until it just dies of exhaustion and boredom. By using our preferred parallel resistor formula, we can solve for the total resistance seen by this source, where a 1 kiloohm resistor in parallel with a 2.2 kiloohm resistor is 687.5 ohms, and then use this value in Ohm's law to solve for the source current, where source current equals the supply voltage divided by the total parallel resistance, yielding 203.6 milliamperes. Again, going to show you that you can solve for the same quantity using several different methods, and, importantly, you should get the same answer regardless of the method. Why do I consider this method the hard way? It's because you have to solve for total resistance using a formula not readily solvable in your head. Notice, using the easy way, I took two currents and added them together. Is adding two numbers easier than performing a weird formula and then Ohm's law? Yes, it is. This being said, you can use either method to check the other, and they should agree. Point of advice regarding your choice of methodologies. Don't continually rely upon one method. Practice everything. You should be able to use Ohm's law and the total resistance formulas with your left hand equally as well as you apply Kirchhoff's voltage and current laws with your right. One-trick ponies make excellent dog food when their one trick is no longer an option. Now let's turn our attention to power distribution inside a parallel circuit. Given an understanding that power input to a system is always equal to power output, it could be stated that the summation of individual power dissipations equals the power input. The power delivered by the source is equal to that dissipated by both the 1K and the 2.2K. In this case, we're assuming all input power is delivered to the individual components and there are no losses to our system. Substituting in the appropriate values, we find power delivered by this source to be 28.5 watts. There is another manner for solving for this same power input. Notably, what is the source voltage times the source current, or any other permutation of the power equation from the perspective of the source? In this case, 140 volts times 203.6 milliamperes again yields 28.5 watts. The same answer from two different perspectives, and they agree. Now, let us consider the magnitude of the power dissipated by individual elements in relation to their resistance value. Given voltage across elements in a parallel relationship is the same, our earlier understanding that the smallest resistance in a parallel relationship draws the most current, and our understanding the power equation that power equals voltage times current, is readily understandable that the element that draws the most current in a parallel relationship, i.e. the smallest resistor, should dissipate the most power. It can just as rightly be said that the element drawing the least amount of current in a parallel relationship, i.e. the largest resistor, dissipates the least amount of power. Identical resistors in a parallel relationship, i.e. ones with the same voltage drop across and the same current through, should probably dissipate equal amounts of power. Is this the case for our circuit? Yes, it is. The 1 kilo ohm resistor is dissipating the most power because it's drawing the most current. And the 2.2 kilo ohm resistor is dissipating the least power because it's drawing the least current. This circuit analysis is all well and good until an additional 2.7 kilo ohm resistor saunters by and enters this parallel relationship. Pause the lecture and ponder this simple question. Does source current go up or does source current go down? Take your time and think about this. Remember, this is not a series relationship. This is a parallel relationship. There are fundamental differences between the two relationships regarding how increasing numbers of resistors inside these circuits affect total resistance. You do not need to resort to calculations to answer this simple question. Will source current go up or will source current go down now that there is an additional path in parallel? Does the 1 kilo ohm resistor care that there is an additional third resistor in this parallel relationship? No, neither does the 2.2 kilo ohm resistor. Both these resistors continue to draw their respective amounts of current, and only the source is aware that it must now provide more current for another electrical load. This again reinforces our earlier understanding of parallel relationships we gained in the fixed resistors lecture. Anytime another resistor enters a parallel relationship, the total resistance seen by the source goes down because there is another path for current. Source current increases because the total resistance decreases. Given this new 2.7 kilo ohm resistor is also in parallel to our original configuration, the voltage across it is also 140 volts. Ohm's law states that the current drawn by this resistor is the voltage across it divided by its resistance. 140 volts divided by 2.7 kilo ohms yields a current draw of approximately 51.9 milliamperes. Given the source was already supplying 203.6 milliamperes to the original parallel combination of a 1 kilo ohm resistor and a 2.2 kilo ohm resistor, it must now supply an additional 51.9 milliamperes. It is easy to see that the current drawn from the source has now increased to 203.6 milliamperes plus 51.9 milliamperes for a total draw of approximately 255.5 milliamperes. With increased current draw, the power supply by the source increases. Power input equals source voltage times source current. 140 volts times 255.5 milliamperes yields approximately 35.8 watts. Given we already calculated for the power dissipated by the 1K and the 2.2 kilo ohm resistor and just solve for our new power input, and we are keenly aware that power in always equals power out. In this case, power in equals power dissipated by the 1K plus power dissipated by the 2.2K plus power dissipated by the 2.7K. We can solve for power dissipated by the 2.7 kilo ohm resistor by substituting in the necessary values. Subtracting 28.5 watts from both sides yields the power dissipated by the 2.7 kilo ohm resistor is approximately 7.3 watts. We can check our work by solving for individual power dissipated by the 2.7 kilo ohm resistor by using voltage across it times the current through it, or any permutation of the power equation. 140 volts times 51.9 milliamperes again yields approximately 7.3 watts, confirming our earlier calculation. Finally, what's the total resistance seen by the source now that there's an additional 2.7 kilo ohm resistor placed in parallel with our original configuration of a 1 kilo ohm in parallel with a 2.2 kilo ohm resistor? Your choice. Do it the long and hard way and use your pick of the parallel resistor formulas, or a quick and easy reconfiguration of Ohm's law, where total resistance equals source voltage divided by source current. 140 volts divided by 255.5 milliamperes yields approximately 548 ohms. Additionally, we can use permutations of the power equations to solve for total resistance, where the total resistance seen by this source is the power input divided by source current squared, or the source voltage squared divided by power input. Again, either formula, you should get approximately 548 ohms of total resistance. Again, I must point out all methods yield the same answer. And if you get this same answer, you can be reasonably certain you're making your lab instructor proud of you. No, not proud. That's definitely not the word I'm looking for. Less ashamed. In this spirit, try not to make this next illustrated example problem a terrible, embarrassing mess. Solve for everything. Voltage across all components, current through all components, power dissipated by all components, current and power supplied by the source. Notice I am not asking you to solve for total resistance, but if you want to do it the hard way, that option is available. Now, before you bebop off into the streets and make a mess of this, let me impart this advice. Voltage across components hooked in parallel should be the same. The sum of currents entering a node should equal the sum of currents leaving a node. What goes in should equal what comes out. Current should be the largest through the smallest resistor in a parallel relationship. Current should be smallest through the largest resistor in a parallel relationship. Current should be the same through identical resistors in a parallel relationship. The smallest resistor in a parallel relationship should dissipate the most power. The largest resistor in a parallel relationship should dissipate the least amount of power. Equal resistors in a parallel relationship should dissipate equal amounts of power. Power input should always equals power out. You can always use Ohm's law, and you can use any permutation of the power equations. Off you go. Have fun storming the castle. Here is a parallel relationship of three resistors. R1 is a 1.5 kilo ohm resistor, R2 is a 1.2 kilo ohm resistor, and R3 is a 6 kilo ohm resistor. They are all supplied by a 60 volt source. Voltage across elements in parallel is the same. V1 is 60 volts, as is V2, as is V3. With 60 volts across a 1.5 kilo ohm resistor, the current through it should be the voltage across it divided by its resistance. 60 volts divided by 1.5 kilo ohms yields a current draw of 40 milliamperes. With 60 volts across a 1.2 kilo ohm resistor, the current through the second resistor should be the voltage across it divided by its resistance. 60 volts divided by 1.2 kilo ohms yields a current draw of 50 milliamperes. The current draw by our third resistor is the voltage across it divided by its resistance. 60 volts divided by 6 kilo ohms yields a current draw of 10 milliamperes. The power dissipated by the first resistor is the voltage across it times the current through it. 60 volts times 40 milliamperes yields 2.4 watts. The power dissipated by the second resistor is the voltage across it squared divided by its resistance. 60 volts squared divided by 1.2 kiloohms yields 3 watts. The power dissipated by the third resistor is the current through it squared times its resistance. 10 milliamperes squared times 6 kiloohms yields 600 milliwatts or 0.6 watts. The power input to this system is P1 plus P2 plus P3. Substituting the calculated values for P1, P2, and P3, we find our power input to be 6 watts. To solve for source current, we can summate the individual currents, where IS equals I1 plus I2 plus I3. 40 milliamperes plus 50 milliamperes plus 10 milliamperes yields a total current draw of 100 milliamperes. Or we can make use of the power equation, where power input equals source voltage times source current, and solve for source current, where source current is equal to power input divided by source voltage. 6 watts divided by 60 volts again yields a current draw of 100 milliamperes. Notice at no time during the course of our calculations did it ever necessitate solving for total resistance seen by the source. However, because we're curious, what's the total resistance that would draw 100 milliamperes from a 60 volt source? Using a reconfiguration of Ohm's law, our total resistance equals our source voltage divided by source current. 60 volts divided by 100 milliamperes yields a total resistance of 600 ohms. Again, exactly as we previously calculated during the warm-up exercises, confirming our analysis is on the right track. That last illustrated example problem should have been pretty understandable. Yes, there's a bunch of calculations in there, and it might be the first time you've ever seen a parallel circuit before, but think about it. It's formulaic. Do this, then do that. It's as repetitious as a reggaeton song, Calle 13 being the notable exception. There is no sense of investigation or experimentation or even mystery about it. It's a complete setup and totally unworthy of aspiring technicians wishing to understand electronics and learn troubleshooting skills. You will never ever see a troubleshooting scenario as easy as this, and if you do, you can plug in a pre-programmed drum beat, come up with some dumb rap while your lab partner does the work for you, because it is very easy to assemble a total setup. Here's another series circuit with the following observed properties. R1 is a 2.4 kilo ohm resistor, R2 is a 4 kilo ohm resistor, and R3 is an 8 kilo ohm resistor. We know all the resistance values, but we don't know the magnitude of the voltage supply. We do, however, know the current through R2 to be 21 milliamperes. I still want you to solve for everything, and I am not giving you any additional information to do so because I already gave them to you. Ohm's law. Voltage across elements hooked in parallel is the same. Pause the lecture and take your best shot at this. Struggle with it a bit and don't tap out too early. There are a couple of different jump-off points for problems like these. However, the easiest way is to go immediately to a spot with two known values. In this case, a known resistance and a known current, and see if I can use these values to calculate another property that may be of interest. I can use the known current value and the known resistance to solve for the voltage drop across this resistor using Ohm's law. V2 equals I2 times R2. What would the knowledge of the voltage across R2 gain me? Aha! A couple of you might be slapping your foreheads right now, but I bet your lab partner is still staring blank-eyed at the screen and drooling on themselves. Yes, knowing the value of the voltage across R2, I am immediately aware that this same voltage drop must appear across both R1 and R3, because voltage across elements hooked in a parallel relationship is the same, and those voltage drops must have come from an equivalent voltage rise. The rest of the problem is not a problem anymore, it's just a duck shoot. With 21 milliamperes flowing through a 4 kilo ohm resistor, V2 is 84 volts. This must also mean that V1 is also 84 volts, V3 is 84 volts, as is our supply voltage, 84 volts. The current through our first resistor is the voltage across it divided by resistance. 84 volts divided by 2.4 kilo ohms is 35 milliamperes. The current through our third resistor is the voltage across it divided by its resistance. 84 volts divided by 8 kiloohms yields 10.5 milliamperes. When R1 draws 35 milliamperes of current, R2 draws 21 milliamperes of current, and R3 draws 10.5 milliamperes of current, it is easy to realize that the sum of currents leaving node A must equal the current entering it. IS, our source current, is therefore equal to I1 plus I2 plus I3. 35 milliamperes plus 21 milliamperes plus 10.5 milliamperes yields a total current draw of 66.5 milliamperes. The power supplied by the source is the source voltage times the source current. 84 volts times 66.5 milliamperes yields approximately 5.6 watts. The power dissipated by resistor 1 is the voltage across it squared divided by its resistance. 84 volts squared divided by 2.4 kiloohms yields 2.94 watts. The power dissipated by the second resistor is the current through it squared times its resistance. 21 milliamperes squared times 4 kiloohms yields 1.764 watts. Making use of the fact that power input always equals power output, it can be stated that power in equals P1 plus P2 plus P3. And having solved for P input, P1, and P2, we can solve for P3 to be 882 milliwatts, or 0.882 watts. We can check our work to find that the smallest resistor draws the most current and dissipates the most power, and the largest resistor draws the least amount of current and dissipates the least amount of power. I'm reasonably confident our answers are correct, and we could proceed with the rest of this lecture. Let's try another illustrated example, this time featuring a little technical forensic examination. We're given extremely sparse information about this parallel circuit, or what remains of it. At one time, this is a 1.2 kiloohm resistor in parallel with a 1.8 kiloohm resistor, both of which were 50 watt wire wound resistors, only one of which now remains. Let's say your lab partner wasn't properly supervised and started pressing buttons they shouldn't have. We're left with the fire blackened remains of a single resistor, and we want to know what happened at the time this circuit bit the dust. In order to make this a solvable problem, we are allowed to make the following assumptions. Let's say the missing resistor totally ignited and instantly melted into slag at 50 watts. This is an obvious overdramatic simplification, because even a 50 watt resistor can handle more than 50 watts before totally igniting and instantly melting into slag. Ask me how I know. But let's say that's how this one rolls. My question to you is twofold. First, which resistor burned up and which resistor rode out the storm in, if not style, survivor mode? What is the 4-band color code beneath that fire blackened exterior? This is a trick question, by the way. A 50 watt wire wound resistor would not use the 4-band color code. It would be about the size of a big old fat highlighter marker and probably have the unknown resistance value and the words 50 watts clearly written on one side. Question 2. What was the voltage across the parallel combination at the time of ignition? And 3. What was the current through and power dissipated by each element at the time of ignition? Let me remind you, you have the skills necessary to solve this. This won't be easy, and it will require some thought. Pause the lecture and think about this. Think about current and power distribution within a parallel circuit. Think about different permutations of the power formula and how they relate to Ohm's law. Recall that within a parallel relationship, the smallest resistor draws the most current. Given voltage across elements hooked in parallel is the same, and power, being the product of voltage and current, is therefore understandable that the smallest resistor within this parallel relationship would dissipate the most power. The resistor that met its early demise was the 1.2 kiloohm resistor. The surviving resistor of this previous parallel combination is the 1.8 kiloohm resistor. It's the largest resistor and must have been dissipating less than 50 watts at the time of its 1.2 kiloohm neighbor's demise. If this remaining 1.8 kiloohm resistor did use the 4-band color code, it would have been brown, gray, red, and gold, assuming a plus or minus 5% tolerance. A 50 watt wire wound resistor of this size obviously wouldn't resort to such deviousness. By wiping away a bit of the fire blackened exterior, we'd see the words 1.8 kiloohms, do not exceed 50 watts, or I will totally ignite and instantly melt into slag, Don't say I didn't warn you. Look at what happened to that guy over there. Serious, 50 watts max, not a microwatt more. Given our understanding of this resistor's unwillingness to exceed 50 watts, it sounds like the missing 1.2 kilo ohm resistor may have been dissipating 50 watts at the time of its sudden disappearance. Use your understanding of the numerous permutations of the power formula to determine the voltage across this 1.2 kilo ohm resistor dissipating 50 watts, as well as the current through it. Dividing by R both sides and taking the square root of both sides, we are left with current equals the square root of power divided by resistance. I'll insert some parentheses to make abundantly clear the order of operations. I am not just taking the square root of power. I am taking the square root of power divided by resistance. The parentheses around the division operator trumps the regular order of operations where powers and roots typically precede multiplication and division. Operations inside parentheses jump to the head of the line like one of those pushy, annoying people from the East Coast in any situation requiring patience and order. The square root of 50 divided by 1.2 kilo ohms yields approximately 204.1 milliamperes. Solving for voltage across this resistor can be done so using another permutation of the power equation, where power equals voltage squared divided by resistance, multiplying by resistance both sides, and taking the square root of both sides, we are left with voltage equals the square root of resistance times power. Again, notice the parentheses. The square root of 50 watts times 1.2 kilo ohms yields approximately 244.9 volts. Or we could use Ohm's law, where the voltage drop across it is equal to the current through it times its resistance, 204.1 milliamperes times 1.2 kilo ohms, again yields a voltage drop of approximately 244.9 volts. Now we know the voltage across and the current through one of the resistors in our previously two resistor parallel network. Obviously, since this was a parallel relationship, that same voltage would have appeared across our surviving resistor. Via Ohm's law, the current drawn by this resistor is the voltage across it divided by resistance, 244.9 volts divided by 1.8 kilo ohms yields a current draw of approximately 136.1 milliamperes. Notice this larger 1.8 kilo ohm resistor is drawing less current. With the same voltage across it, it should mean that it's dissipating less power. Let's see if that's the case. Using any permutation of the power equation, we find a 1.8 kilo ohm resistor with 244.9 volts across it, drawing 136.1 milliamperes of current, dissipates approximately 33.3 watts. No wonder this 50 watt rated resistor could ride out a 33.3 watt storm. Thanks to our knowledge of basic parallel circuit properties, the case of the missing resistor is now closed. Again, that last illustrated problem should have been readily solvable given your understanding of voltage, current, and power distribution inside a parallel circuit. Some of the questions being asked in this and the previous example problems did not require any calculations, but rather gauge your feeling of how circuits like these operate. Does more or less current flow through larger or smaller resistors with the same voltage drop across them? Does source current increase or decrease as resistors are added or removed from a parallel relationship? Remember, parallel circuits behave differently than series circuits and have easily identifiable characteristics that can be used to your advantage and check your work when performing circuit analysis. Before we wrap up this lecture, I promise we'll compare and contrast the two. We've got to discuss the influence of opens and shorts inside parallel relationships, instrumentation used in parallel relationships, as well as parallel circuit applications. Let's move into a brief discussion about the effects of opens and short circuits inside parallel relationships. An open element in a parallel relationship will disconnect that element from the parallel relationship. Current through that element and that element alone will cease. Will this affect the remaining elements in the parallel circuit? No. They are still connected between the two nodes that define our circuit and are unaffected by the removal or attachment of any other electrical load, at least in a mathematical sense. We'll discuss observed real-world nonlinearities when we discuss series parallel analysis. If current through a single element ceases, and all elements in the remaining parallel combination continue to draw their rated current, How will an open element affect source current? Obviously, with decreased current draw, the source current should go down because with the removal of a path, the total resistance seen by the source will go up. Consider our first example scenario, in which the parallel combination of a 1 kilo ohm resistor and a 2.2 kilo ohm resistor is supplied by a 140 volt source. The 1 kilo ohm resistor is drawing 140 milliamperes of current from the source, and the 2.2 kilo ohm resistor is drawing approximately 63.6 milliamperes of current. It can be said that the source current is I1 plus I2, or approximately 203.6 milliamperes of current. If the 2.2 kilo ohm resistor was to lose connection with our parallel circuit, current through it would cease. And without current flowing through it, there would be no voltage drop across it via Ohm's law. V2 equals I2 times R2. 0 amps times 2.2 kilo ohms yields a 0 volt drop. This being said, since there is a voltage rise, there would still be a voltage drop across the open. With no current flowing through the second resistor, the only element drawing current would be R1. In this case, it is easily understandable that source current drops to 140 milliamperes because the removal of one of the parallel paths increased the total resistance. Consider now an open in another place. What would happen if an open occurred between the source positive terminal and our parallel circuit? Or similarly, an open between the bottom node and the negative terminal of our source. This is no longer a single open element. In this case, this is an entirely open circuit. Current through the whole circuit ceases since there is no complete path from our source through our parallel combination. No current will flow through either element and no voltage drop will occur across either element. The voltage drop will occur across the open. Obviously, with no current drawn by any element, the source will provide no current. Let us now consider the influence of shorts inside parallel relationships. A short is a 0 ohm resistance. If a short is placed in parallel with a single element inside a parallel relationship, and in fact that whole parallel relationship is removed from consideration by becoming a 0 ohm path. This is to be generally avoided because a circuit with 0 ohms of resistance presents no opposition to the source, and current will spike to great magnitudes. Mathematically, we would expect infinite current with 0 ohms of resistance, but this isn't really the case. Let's say the resistance of our shorted parallel combination can be simplified as a 100 milliohm or 0.1 ohm resistor. However, this 140 volt source now has a circuit breaker that opens at 8 amps placed in series with it and the circuit. What will happen? In this case, the current would still theoretically spike to an astronomically high value, where 140 volts opposed by 0.1 ohms of resistance would yield a current draw of 1,400 amps. However, the circuit breaker, experiencing a current draw in excess of 8 amps, is going to shut her down by opening the whole circuit. In this case, a short, ordinarily associated with large current draw, precipitated an open, ordinarily associated with no current draw. And if you think about it, that's the point of the circuit breaker. It detected an abnormally large current draw and prevented it from burning down the house by opening the whole circuit. Good job, circuit breaker. Thanks for saving the day. This is in contrast to a current-limited power supply. If you'll recall, current-limited power supplies, as well as the difference between constant voltage mode and constant current mode, were introduced in the Lab Practices Intro to Power Supplies lecture available at the Big Bad Tech channel. Let's say you're using a benchtop power supply in a lab environment that is current limited to 500 milliamperes. Ordinarily, the parallel combination of a 1 kilo ohm resistor and a 2.2 kilo ohm resistor would draw 203.6 milliamperes, well within this current limited power supply's operational range. If, however, the addition of a low resistance path in parallel with these two resistors dropped the total circuit resistance to 0.1 ohms, the source current would again spike. However, the source would quickly enter constant current mode and only provide a maximum of 500 milliamperes by dropping the output voltage. What's the voltage necessary to push 500 milliamperes through a 0.1 ohm resistor? chances are it'll be super small. Ohm's law states that voltage is equal to current times resistance. 500 milliamperes times 0.1 ohms yields an output voltage of 50 millivolts. Again, the current limited power supply detected an abnormally large current draw and prevented it from burning down the house by dropping its output voltage to keep current draw below a certain maximum preset. In this case, the short circuit is dissipating 25 milliwatts of power. Current is still flowing through the circuit, it just doesn't have a 140 volt punch anymore. Good job, current limited power supply. Thanks for saving the day. Let's now briefly discuss how common electrical instrumentation is employed within a parallel circuit. Recall from the lab practices lectures featuring DMMs employed in voltmeter and ammeter mode, available at the Big Bad Tech channel, the fundamental difference between voltmeters and ammeters is that of across versus through. Voltmeters measure voltage across 2 points and are employed in parallel. Ammeters measure current through a single point and are employed in series. To measure voltage across a purely parallel combination of any number of elements, a single voltage measurement would suffice. Voltage across elements in parallel is the same. Isn't that convenient? What's not so convenient is the use of an ammeter within a parallel circuit. Ammeters measure current through elements and necessitate breaking the circuit and inserting the ammeter in series. This circuit with 3 elements in parallel has only 2 nodes, but there exist a number of different current measurements, notably the source current IS, I1, I2, and I3, where IS, entering node A, splits into I1 plus I2 plus I3 and recombines at node B. What goes in must come out, and what goes out must come in. To measure source current, one would have to turn off the power supply, break the circuit, and insert an ammeter, such that all conventional source current flows out of the power supply positive terminal into the ammeter and the ammeter only, and out of my ammeter and into node A, which, if you think about it, is the trailhead for 3 separate trails. In this case, all source current, regardless of its intended destination, must pass through this single hoop, and there is no way any current can sneak around, under, over, or squeeze by the side of this ammeter. If you think about this at the nodal level, node A has the ammeter outdoor and all 3 high leads of all 3 resistors connected to it. The indoor, the ammeter, necessitated the introduction of another node, which I'll call A prime. A prime is connected to the positive lead of the voltage source, and the indoor, the ammeter. Notice that node A and A prime are not the same node. If the ammeter indoor was connected to the outdoor, the ammeter would be bypassed and the source current would not flow through the ammeter. A and A prime are 2 totally different nodes, and the only way to get from A prime to A is through the ammeter. Additionally, we can measure source current in an alternate fashion. Both placements will read the same value. Let's say this ammeter reads a source current of 100 milliamperes. We'll return our parallel circuit to its original configuration and use an ammeter to measure the current through resistor 1 and resistor 1 only. This again necessitates turning off the power supply, breaking the circuit at our chosen point of insertion, inserting the ammeter in series with resistor 1. As source current flows from our source and enters node A, the current bound for resistor 2 and 3 continues on its merry way. However, the current bound for resistor 1 goes into the ammeter and the ammeter only, out of the ammeter, into the high lead of resistor 1 and resistor 1 only, out of resistor 1 and into node B, rejoining I2 and I3, which recombine into the source current and continues on to the negative terminal of our source. If you think about this on a nodal level, this again requires the insertion of an additional node, which I'll call X. The only way to get from A to X is through the ammeter. Notice the emphasis and care I'm spending on the systematic placement of ammeters inside parallel networks. The ammeter, if you think about it, is creating a series parallel relationship, and that all 3 branches are still in parallel with one another. However, the branch on the left now contains an ammeter in series with R1. An ammeter deployed in this fashion will read the current through R1 only, and that's the point. Let's say this ammeter reads 40 milliamperes. Let's try this same exercise with R2. Only this time we're going to break the circuit at the low lead of resistor 2 and insert the ammeter below stream of R2. You can do this. Ammeters go in series with the element they're intended to measure current through. Current inside series paths is the same. It just so happens that this series path containing R2 and the ammeter is placed in parallel with two other paths. Let's say this ammeter reads 50 milliamperes. Finally, let's consider proper placement of an ammeter to measure current through R3. Pause the lecture and see if you can draw this one out. There are several versions of right answers, some more efficient than the next. If you even attempted to break this circuit and insert the ammeter, you're working harder, not smarter. The truth is, you do not need to measure the current through R3. We measured the source current to be 100 milliamperes. We measured the current through R1 to be 40 milliamperes. We measured the current through R2 to be 50 milliamperes. What's left over? The answer is I3. If 100 milliamperes enters node A and 40 milliamperes of it travels through R1 and 50 milliamperes travels through R2, subtracting 90 milliamperes from both sides, we obviously realize that the remaining 10 milliamperes of current has to travel through R3. Don't even worry about taking this current measurement because what comes in must comes out. Consider an occasion where you're pressed for time. You want a current measurement through R3 as quick as possible. But let's say R3 is inaccessible and cannot be modified. Measure the source current as previously. Again, assume we see 100 milliamperes of source current. Now consider the placement of an ammeter in the following fashion. This ammeter is not reading current through an individual element anymore, but rather the current bound for both R1 and R2 is traveling through it. In this case, the ammeter would read I1 plus I2, or 90 milliamperes. What's I3? If IS equals I1 plus I2 plus I3, and we measured I1 plus I2 in one lump sum to be 90 milliamperes, we can solve for I3, again to be 10 milliamperes. We don't know exactly what I1 is, nor do we know I2, but we don't care. We want to know I3. For all intents and purposes, R1 and R2 could be a single imaginary resistor that happened to draw 90 milliamperes of current. We'll return to such visualization and analysis techniques when we discuss Kirchhoff's current law and the current divider rule in detail. Finally, consider the ill effects of improper placement of an ammeter inside a parallel circuit. With your newfound appreciation of shorts inside parallel circuits and the understanding that an ammeter can be modeled as a 0 ohm resistance, is this any way to win your lab instructor's adulation or respect? No. This is a one-way ticket to an extended session in the iron chair. Ammeters never go in parallel to anything. They always go in series. An ammeter employed in such a fashion shorts out the entire parallel combination, and current will spike to great magnitudes since the resistance of this combination is so low. Don't do this, or you'll damage the meter, your circuit, your source, or yourself. Ammeters measure current through something and are never employed in parallel. Let's briefly discuss applications of parallel circuits. Keep in mind we've yet to cover some details about parallel circuits in any degree of depth, so this list will be pretty short. We'll talk about residential electrical distribution, batteries, generators and generator synchronization, shunt-wound DC motors, and finally, not elements nor sources in parallel, but rather switches in parallel. Consider electrical distribution within a house. In the United States, residences are typically supplied by 240 volt, single phase, 60 Hz AC. Some branch circuits like stoves, dryers, washers, or other heavy-duty equipment require 240 volt supply voltage. The 240 volt input, however, can be split into two legs of 120 volt AC and then subdivided into branch circuits, each at 120 volts AC. You may not understand all the terminology I threw in there, but let's use this simplification. Here's a 120 volt DC branch circuit supplying multiple outlets and a couple lights inside a room. All the outlets, since they're in parallel, provide 120 volts to whatever is plugged into that outlet, and they don't affect each other. A radio designed to be run on 120 volts gets 120 volts from the first outlet, as does a heater or anything you plug into any of the remaining outlets, because they're all hooked in parallel to the 120 volt source. Notice the parallel branches, including the lights, have switches in series with the lights. The lights won't light if the switch is open, nor will any outlet draw current if there's nothing plugged into the outlet. The source will experience an increasing current draw. As more and more source current is being drawn, the circuit breaker is becoming closer and closer to its operating point. At some point, that last hairdryer, microwave, radio, electric blanket, blender, computer, fan, heater, or lamp is going to draw current in excess of the maximum permissible 20 amps from the source. And the circuit breaker will open, and the whole room will go dark because you dropped the total resistance of that room too low and the current to that branch circuit went too high. This might explain what I'll call electrical anomalies experienced by those individuals that live in old houses, remodeled houses, or houses simply wired by rummies, junkies, or tweakers. When the circuit breaker for your kitchen pops, does it turn off your bedroom lights? It shouldn't. This is known as functional isolation, in that parts of a circuit or a system are protected from the failure or malfunction of associated or contiguous parts. Ideally, each bedroom, bathroom, kitchen, garage, heating or cooling system, or room should function independently of one another. Each item inside a branch circuit is wired in parallel, and stepping up one level, all the branch circuits with their circuit protection means are wired in parallel with one another. The main breaker services the whole residence. Each single breaker services one room or one subsystem. Additionally, residences can feature a sub-panel, for example, feeding a garage that connects or disconnects all branch circuits inside the garage only with the main supply. Individual breakers leading from that garage sub-panel can then be used to functionally isolate these branch circuits. You should be able to shut down a system in a logical order, allowing necessary maintenance procedures to be performed without compromising functionality of the whole system. Imagine if you had to shut off the whole International Space Station to fix an outlet in some astronaut's bedroom. Ideally, you should be able to shut down just that bedroom and keep the rockets rocketing, the heaters heating, the air pumps pumping, and the Tang cooler tangy. Returning back to our residential electrical distribution example, consider the predictability offered by proper functional isolation. If the breaker that says all kitchen outlets is off, every outlet in the kitchen should be off. If there's an outlet in your kitchen that's actually part of the bedroom circuit and the breaker servicing the bedroom branch circuit is closed, that outlet in the kitchen is live. Do not assume everything you see in one room is part of one circuit. Water heaters, typically 240 volt AC loads, are normally wired independently from the 120 volt AC bathroom outlets and light circuits. The point is, assume nothing, trust no one, always test and verify. You must properly lock out, tag out, and test and verify that all sources of hazardous energy are not present, nor can any build up during the course of your maintenance procedures. Again, returning to the electrical anomalies observed in less than ideal residential settings, should an electrical load designed to run on 120 volts experience less than 120 volts? It shouldn't. Electrical loads in a perfectly parallel relationship should experience 120 volts. Does turning on or off one electrical load affect another in a perfectly parallel relationship? It shouldn't. I'm of course referring to electrical loads not wired in parallel, but rather in series with one another. Two identical light bulbs in series with each other would not experience a 120 volt drop as required if they were wired in series, but rather 60 volts as dictated by the voltage divider rule or any implementation of series properties and Ohm's law. These bulbs might be unusually dim, if they worked at all. If the filament of one light bulb in a series relationship opened, current through that light bulb would cease, as would current through everything in series with it. Electrical loads typically aren't wired in this fashion. Ideally, every electrical load designed to run on 120 volts receives 120 volts because they're all wired in parallel with one another. You can think of each load as a rung in a ladder, one load and one load only per rung. We'll return to this topic when we discuss ladder logic diagrams, a common method of schematic drawing utilized in motor controls. Now let's consider not electrical loads in parallel with one another, but rather electrical sources in parallel. Provided each electrical source is of the same voltage, the addition of electrical sources in parallel simply increases the available power output by increasing the amount of available current. Allow me to demonstrate. Consider a string of 96 3.7 volt lithium-ion batteries in series with one another. Each battery is limited to supplying, let's say, 105 amps. Therefore, this string of 96 batteries in series will have a total voltage of 96 times 3.7 volts, or 355.2 volts. However, since current in series relationships is the same, the maximum current capable of being safely produced by this whole string is 105 amps. If our adjustable load resistor was drawing 105 amps from this 355.2 volt source, the source would be delivering 355.2 times 105 amps, approximately 37.3 kilowatts. How could this battery pack provide twice as much power, yet still operate at 355.2 volts? The answer is it can't. However, two of them in parallel could. A parallel combination of two strings of 96 3.7 volt batteries would still have 355.2 volts across them. However, two parallel strings are now capable of safely delivering 105 amps each for a total combination of 210 amps. Both sources would in effect be supplying approximately 37.3 kilowatts each for a total input of approximately 74.6 kilowatts. You want 3 times as much power? Put three 355.2 volt strings in parallel, each capable of supplying 105 amps individually. The total current supplied to this load is 315 amps at 355.2 volts for a power input of close to 111.9 kilowatts. This is a lot of power and represents a simplified version of the configuration of 3 series strings of 96 3.7 volt lithium-ion batteries placed in parallel with each other inside the original Chevy Volt. The peak output of the original Chevy Volt's electric motor is actually 111 kilowatts, so I've taken obvious liberties with the current capable of being produced by the parallel string to make things simple. I sincerely doubt the inner workings of this vehicle is 99.2% efficient at peak power. We'll return to motors and the maximum power transfer theorem in later lectures. The point is, losses will always occur, and you need to anticipate these losses in system design. This also goes to show that voltage sources identical in magnitude placed in parallel with one another simply provide an increased current range in the case of extreme demand. Additionally, in the event of moderate current demand, each source in parallel will experience a current draw inversely proportional to the number of sources providing current. In this case, the electrical load still draws its required current from the available 355.2 volts. However, it's just drawing that current from 3 different places. Many hands make light work. Parallel arrangements of battery banks ensure that no one series string of batteries is unnecessarily depleted, a situation which shortens the operational lifespan of a battery, as we'll learn in later lectures. Let's think on a grander scale and talk about large-scale generators placed in parallel and something called generator synchronization. This example makes use of some obvious oversimplifications, but consider a hydroelectric dam with a number of turbines, some operating and some at the ready. Hydroelectric dams are neat because they represent both reliable base and responsive peaking power, all based off of renewable energy. A given number of turbines can operate as a predictable base. As demand increases, additional turbines are brought online in parallel to meet peak demands. Consider a bad day at the dam, however, in which a generator is improperly synchronized with that of the grid. I know we haven't gone into AC yet, but realize AC voltage has a magnitude, a frequency, and a phase shift. And if a generator is to be properly placed in parallel with the grid, it must have the same magnitude, the same frequency, and the same phase shift as the grid at the moment of synchronization. Otherwise, a differential between the grid and that generator will be experienced. AC is its own strange animal, but consider at the moment of synchronization, the grid having one value and the generator being brought online another because of one of three undesirable scenarios. 1. The generator could have the correct frequency and the correct phase shift, but the wrong magnitude. At the moment of synchronization, a differential would exist. 2. The generator could have the correct magnitude and the correct phase shift, but the wrong frequency. At the moment of synchronization, a differential would still exist. Finally, the generator could have the correct magnitude and the correct frequency, but the wrong phase shift. At the moment of synchronization, a voltage differential would exist. Recall from the basic Kirchhoff's voltage law lecture, available at the Big Bad Tech channel, that voltage sources with differing magnitudes in parallel with each other are to be avoided at all costs. Not only will the larger voltage source discharge into the smaller source, such a poorly timed synchronization event will also create a mechanical disturbance in addition to the undesirable electrical events. Consider a rotor lagging ever so slightly behind or leading ever so slightly ahead of the desired synchronization position. This rotor could suddenly be motored forward or brake backwards at the time of synchronization, often with catastrophic mechanical results. Don't be the dude with your hand on the switch when this happens, because you should know that voltage across two elements placed in parallel with each other should be the same. We'll return to generators, generator synchronization, the grid, and transmission topics in later lectures at the Big Bad Tech channel. Fair warning, it's not nearly as easy nor nearly as pretty as the little cartoons I've drawn and the gross oversimplifications I've made. Here's another far simpler application of parallel circuit properties. This application is a shunt-wound DC motor. A shunt, as the name implies, is a path in parallel to another path. Recall at the very end of the basic Kirchhoff's voltage law lecture, I introduced the separately excited DC motor, where the field and armature windings are supplied by two totally separate voltage sources. You should be jumping out of your skin right now at the sheer stupidity of such an arrangement, because you're readily aware that you don't need two sources to provide voltage to two separate elements when a parallel combination of two elements and a single source will do the same job quite nicely. A shunt-wound DC motor is where the field, the stationary portion of the motor, is placed electrically in parallel with the armature, which is the rotating portion of the motor. Compare and contrast these two types of DC motors. There are advantages and disadvantages of both configurations. What if you wanted to vary the armature and the field voltages separately? You could not do this using a shunt-wound DC motor because the voltage across components hooked in parallel is the same. This ability to independently vary field and armature voltage for a separately excited DC motor comes at the obvious expense of having to include another voltage source. Yes, the field and armature windings of a shunt-wound DC motor are interrelated. This device will have different torque and speed characteristics than that of an independently variable, separately wound DC motor, but this comes with a major advantage. Namely, you only have to use one source to power a shunt-wound DC motor. We'll return to DC motors, the various configurations of field and armature windings, and how current through and voltage across the field and armature windings affect the torque and speed characteristics in later lectures. For now, realize both the armature and the field winding of a shunt-wound DC motor experience the same voltage because they are in parallel with one another. Lastly, consider an application of parallel circuits involving neither loads nor sources in parallel, but rather switches placed in parallel. Consider an electrical load, be it a lamp, a motor, a buzzer, a solenoid, or a coil, modeled as a resistor placed in series with a set of switches that are in parallel with one another. I'll call them switch A and switch B. Which switch operates the load? If switch A is closed, current can flow from my source through my load. If switch B is closed, current can flow from my source through my load. In fact, if I press both switch A and switch B simultaneously, current can flow from my source through my load. The only way the load will not operate is if I don't close either switch. The answer is either switch A or B, or both simultaneously, will supply current to my load resistor. This is the logical OR function, and it is something we'll discuss in later lectures on motor controls and digital electronics at some length. An application of the OR function might be the ability to operate the desired electrical load from one of several different locations. Switches electrically placed in parallel with one another enable this possibility. We are just about to bring this lecture to a close, but before we do, let's review the checklist for both series and parallel circuits and compare and contrast the two. This is an extremely valuable exercise and will ideally correct any lingering misconceptions you may have about these two similar but totally different electrical relationships. Let's start with some universally acceptable analysis techniques, notably Ohm's law and the power equations. Regardless of the flavor, color, or sexual orientation of the circuit you're performing an analysis on, you should be able to whip out any permutation of Ohm's law or the power equations to arrive at any answer you seek. Notably, the current through something is the voltage across it divided by resistance. The voltage drop across something is the current through it times its resistance. The resistance of something is the voltage across it divided by the current through it. The power dissipated by any element is the voltage across it times the current through it squared times its resistance, or the voltage across it squared divided by its resistance. If we were to use the power equations from the perspective of a source, we could say the power supplied by the source is the source voltage times the source current squared times the total resistance, or the source voltage squared divided by total resistance. Additionally, we can always make use of the simple and powerful statement that power input to a system is always equal to power output, regardless if the circuit is a series parallel, or some crazy complex circuit you've never seen before. All of these basic properties should hold true. Ohm's law, the power equations, power in always equals power out. Now, let's paint a line down the center of the gym and put all purely series properties on one side and all the purely parallel properties on the other, and have them knock the hell out of each other in an especially vicious game of dodgeball. Current through elements in series is the same. Voltage across elements in parallel is the same. Kirchhoff's voltage law is an especially useful circuit analysis technique for series circuits. The sum of voltage rises should equal the sum of voltage drops. What goes up must come down. Kirchhoff's current law is an especially useful circuit analysis technique for parallel circuits. The sum of currents entering a node should equal the sum of currents leaving a node. What goes in must come out. Series circuit analysis employs a handy shortcut called the voltage divider rule. Parallel circuit analysis employs a handy shortcut called the current divider rule, which I'll introduce in the near future. The largest resistor in a series relationship has the largest voltage drop and dissipates the most power. The smallest resistor in a parallel relationship has the largest current through it and dissipates the most power. The smallest resistor in a series relationship has the smallest voltage drop and dissipates the least amount of power. The largest resistor in a parallel relationship has the smallest current through it and dissipates the least amount of power. Equal resistors in a series relationship have equal voltage drops and will dissipate equal amounts of power. Equal resistors in a parallel relationship have equal current draw and dissipate equal amounts of power. Adding resistors in a series relationship decreases source current draw because the total resistance increases via the series summation of resistances formula. Adding resistors in a parallel relationship increases source current draw because the total resistance decreases via your choice of several parallel resistance formulas. A shorted element in a series relationship will remove the shorted element only from consideration. No current will flow through the shorted element and no voltage will be dropped across it. The total resistance will go down and source current will go up. An open element in a parallel relationship will remove just the open element from consideration. No current will flow through the open element and no voltage will be dropped across it. The open element will no longer draw current from the source and source current will decrease. An open inside a series relationship will cause all current through the series circuit to cease. A short inside a parallel relationship will cause current to dramatically and potentially catastrophically increase. The comparison between the two basic electrical relationships, series and parallel, is now complete. And I swear we are just about done with this lecture, but I am going to take the unusual step of reaching out of the internet and grabbing you by the collar with both hands and shaking the living daylights out of you. Pay attention, because I am about to blow your mind. I have nothing left to teach you. The rest is just party tricks. These series versus parallel properties are always true, and their application to circuit analysis and troubleshooting must become real, visceral, and instinctual. This cannot be accomplished by watching an online lecture or playing around with circuit simulation software. You must get inside a hardware lab and practice and apply these techniques on real-world components using real-world instrumentation. You will make mistakes, and things will not go smoothly at first. But realize elements in series with one another must necessarily carry the same current through them, and elements in parallel with one another must necessarily have the same voltage across them. The sum of voltage rises will always equal the sum of voltage drops. What goes up must come down. The sum of currents entering a node must equal the sum of currents leaving a node. What goes in must come out. Any iteration of Ohm's law or the power equations is always true, as is the incredibly simple and useful observation that power in always equals power out. Here is the especially crazy part. These facts are true for all circuits, including those not purely in series nor purely in parallel. All basic circuit analysis techniques can be boiled down to these simple observations. And the only essential point I can add to this checklist is this bit of personal advice. Visualize circuits from the perspective of flowing current. If current has no choice but to flow through a single path, elements in that path are in series with one another. If current has a choice between paths, these paths are in parallel with one another. Notice the slight twist in phrasing I've employed by saying path instead of element, implying that these properties of purely series and purely parallel circuits can be extrapolated into larger and more complex circuits, including DC series parallel circuits, AC series circuits, AC parallel circuits, and AC series parallel circuits, and more. I know this lecture's title is Basic Parallel Circuit Properties, and not a sudden jump to advanced series parallel analysis techniques, but consider the simple utility of these basic pure series and pure parallel properties. What I've drawn here is two series parallel circuits. Let's consider a basic analysis of the top series parallel circuit using the perspective of flowing current. Source current leaving our source's positive terminal enters node A. At node A, current has a choice to travel through R1 or R2. R1 and R2 are clearly in parallel with one another. However, as the current from R1 and R2 recombine at node B, this single stream of current has no choice but to travel through R3 to get to node C and the negative terminal of our source. It can be said that R3 is not in series with R1, nor R2 singly, but rather R3 is in series with a parallel combination of R1 and R2, something I'll call R prime. The total resistance seen by this source is R prime plus R3. Substituting the value for R prime, we find the total resistance seen by the source is the parallel combination of R1 and R2 in series with R3. The parentheses imply you must first calculate R prime, then use it to find RT. Now, let's consider voltage and current distribution within this circuit. What is the voltage drop across R1 compared to that of R2? The voltage drop across elements hooked in parallel should be the same. If we were to model the parallel combination of R1 and R2 as an imaginary resistance called R prime hooked between node A and B, how would the current through R prime compare to that of the current through R3? The current through elements hooked in series is the same. Using Kirchhoff's voltage law, we can examine the voltage distribution of this series parallel circuit. Start here. Travel in this direction. There is a voltage rise of E. There is a drop of VAB. There is a drop of VBC. Given both resistors R1 and R2 are hooked between node A and B, I can rewrite the Kirchhoff's voltage law equation as follows. As E equals V1 plus V3, or E equals V2 plus V3. V1 equals V2, and if we were to use our imaginary resistance R prime, the voltage drop across R prime is equal to V1, which is equal to V2. For an additional iteration of our Kirchhoff's voltage law, as E equals VR prime plus V3. Notice at no time did I introduce any new conceptual understanding to the analysis of this seemingly advanced series parallel circuit, but rather used basic properties of series and parallel circuits, notably that current in series paths is the same, voltage across elements hooked in parallel is the same, and our understanding of Kirchhoff's voltage law in that what comes up must necessarily come down. This being said, let's apply Kirchhoff's current law, a relatively newly introduced property to this circuit. What goes in must come out. If the current through R1 and the current through R2 recombines at node B, it can be said that I3 equals I1 plus I2, since there are no other additions nor subtractions to this path. What goes in must come out. If I3 travels into the negative terminal of our source, it must come out of the positive terminal of our source, and entering node A, it must proportionally split into I1 and I2. What comes out must necessarily have come in. Additionally, it can be stated that I3, the current through R3, is also our source current, IS, and this source current is proportional to the supply voltage E and inversely proportional to the total resistance via Ohm's law. IS equals E divided by RT. We could rearrange this equation to solve for RT, where RT equals source voltage divided by source current, where RT must necessarily be our original calculation of RT, R1 in parallel with R2, and then taken in series with R3. I must reiterate, I have not introduced any esoteric weirdness, legal mumbo-jumbo, nor double secret black magic. All these properties kind of make sense if you visualize circuits at the nodal level and from the perspective of flowing current. Finally, and this is important, at no time Was it absolutely necessary for me to solve for total resistance, to make use of basic pure series and pure parallel properties? Although this could be done, current through R prime should equal current through R3, and the voltage drop across R prime plus the voltage drop across R3 should equal our total applied voltage. Any further simplification beyond a purely series circuit with two elements is like taking apart your car to find a quarter under the seat. Just look under the seat. This being said, I issue you a challenge. I dare you to pause the lecture and perform an analysis of this second series parallel circuit and determine the following. What is the relationship of E, V1, V2, and V3? Meaning, are any of these values equivalent to one another, or do any of these values summate to other values? What is the relationship of source current IS to that of I1, I2, and I3? Meaning, are any of these current values equivalent to one another, or do any of these values summate to other values? This may seem challenging at first, because we've only had the briefest introduction to some of these properties, but realize there is no numbers in this problem. All I'm asking you to do is, again, visualize this circuit at the nodal level and from the perspective of flowing current. Current through elements hooked in series is the same. Voltage across elements hooked in parallel is the same. For every rise there is a drop, and what goes in must come out. Pause the lecture and take a shot at this. Fortune favors the bold. Again, you might find it extremely helpful to reduce this series parallel circuit to a purely series or a purely parallel simplification and no further, and then just apply basic series and basic parallel properties. The bold and daring among you may have come up with the following analysis, not necessarily in this order. In this circuit, flowing source current enters node A and has a choice to travel through two paths. These two paths are clearly in parallel with one another. One of the paths is just R3. However, the left path has R1 and R2 clearly in series with one another. Once current leaves node A and travels through the left branch, it has no choice but to travel through R1 and R2 in series. It can therefore be stated I1 equals I2. Since source current is splitting as it enters node A, it can be said that the source current is equal to the summation of I1 plus I3 or I2 plus I3, since I1 equals I2. Additionally, since we are aware that R1 and R2 are in series with one another, we can think of this left-hand branch as being a single imaginary resistor, which we'll call R double prime, where R double prime is a series combination of R1 and R2. If we wanted to solve for the total resistance seen by this source, it is clearly R double prime in parallel with R3, where R double prime is a series combination of R1 and R2. Again, the parentheses imply you must first calculate R prime, then take that in parallel with R3 to solve for RT. We do not need to perform that level of simplification though, because we want to apply the properties of purely series or purely parallel circuits. Using our two resistor simplification, we're clearly left with a purely parallel circuit, where the voltage drop across R double prime is equal to that of the voltage drop across R3. And since the source E is hooked to this same two nodes, E equals VR prime, which equals V3. If R double prime is in actuality R1 in series with R2, it would stand to conjecture that those resistors that compose R double prime should drop representative portions of VR double prime. If we were now to crack open R double prime to be the series combination of R1 and R2 and apply Kirchhoff's voltage law, starting here and traveling in this direction, we rise E, fall V1, fall V2, which should equal the fall V3. These last two examples may have been challenging because this might have been the first time you've seen a series parallel circuit. Trust me, it will not be the last. However, all the basic series and parallel properties should hold true. If you observe contradictions, you're performing the analysis wrong, you're making wrong observations on the correct circuit, or you're making correct observations on the wrong circuit. All right, I do believe we've covered what I've intended to do in this lecture and more. Keep in mind, we've yet to cover Kirchhoff's current law and the current divider rule, both handy weapons in your ever-increasing arsenal. In conclusion, this lecture took a close look at parallel circuits. We learned that voltage across elements hooked in parallel is the same and made use of this incredibly simple statement to determine unknown properties based off of limited observations. We had an introductory discussion about Kirchhoff's current law and learned that what goes in must come out. We discussed shorts, opens, and instrumentation inside parallel circuits. We discussed applications of parallel properties, including residential electrical distribution, generators and generator synchronization, shunt-wound DC motors, and the logical OR function. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.